Let's consider this one. This again was asked for 4 marks. It's a very simple one again. In the given figure, which is a shape of an A, alphabet A, the first alphabet of your English, we are seeing that you are having 5 resistances that are connected. That is 2 across one length of A, second 2 across the another arm of A, and 1 resistance between the 2. So total 5 resistances that are connected in the shape of A. And you are asked to find out the resistance between X and Y and the resistance between A and B. So if I'm saying that I have to find out the resistance between X and Y, that means my positive terminal is at X, negative terminal is at Y. Same way with A and B, positive terminal at A, negative terminal at Y. First, let's consider just the equivalent circuit diagram for this. Equivalent circuit diagram can be constructed as shown here. We see that we have one resistance which is again getting split up into 2 and then passing forward to another resistance till such time it reaches terminal B. So between terminal X and Y, we see that there is a parallel combination which is in series with another 2 set of resistances which gives you A and B. So total resistance between X and Y. The total resistance between X and Y is given as 1 upon R is equal to 1 upon 6 plus 1 upon 3, which works out to be 1 plus 2 divided by 6, which is nothing but 2 ohms. So I get the resistance between X and Y as 2 ohms. The total resistance between A and B now, which I said that you have another 2 set of resistances which are in series with it. So I get total resistance between A and B as total resistance equal to 3 plus 2, which I have earlier obtained, plus 3, which works out to be 8 ohms. So therefore, the total resistance between A and B is 8 ohms, and that between X and Y is 2 ohms. You are given a circuit again, and then in this circuit we are given a switch K that is closed, and you are asked to calculate the current I, I1, I2 and the voltmeter reading. Now see, you are given these different resistances that are connected in parallel as well as series. You are given a voltmeter that is connected across the series resistance, and there is a key that is being supplied which makes or breaks the electric circuit. It's like a switch. So the moment you keep the key closed, the current is going to flow through it. The moment you keep the key open, the circuit is broken. So they're saying that the switch is kept closed. That means the current is made to flow through the circuit. You have to first find out the equivalent resistance for the parallel network. So I get equivalent resistance for parallel network is R1 R2 upon R1 plus R2. As I said, it is LCM and reciprocal. So if I substitute the value, I get 8 multiplied by 2 divided by 8 plus 2, which works out to be 1.6 ohm. So I get the resistance in parallel as 1.6 ohm. This particular resistance is in series. Is in series with which resistance? The 2.4 ohm resistor across which the voltmeter is connected. So I get the total resistance over here as 1.6 plus 2.4, that is 4 ohms. Getting the total resistance, I have the Ohm's law relation here as current is equal to total voltage upon total resistance. So if I substitute, I get 6 divided by 4, that is nothing but 1.5 ampere. Second part, they are asking me to find out the voltmeter reading. In order to find out the voltmeter reading, I have Vp is equal to I into Rp. So I'll get that as 1.5 multiplied by 1.6, which lands up to 2.4 volt. So I get the voltage across the parallel network as 2.4 volt. But Vp is equal to I1 R1 also. Vp that I have is equal to I1 R1 also. As a result, I1 is equal to Vp upon R1. As a result, I1 is equal to Vp upon R1. So if I substitute here, I get 2.4 divided by 8, which works out to be 0.3 ampere. That means the current that is flowing through I1 is 0.3 ampere. Secondly, I have to find out I2 also. So I go on similar lines. Similarly, I2 will be equal to Vp upon R2. If I substitute over here, it works out to be 2.4 divided by 2, which works out to be 1.2 ampere. Now we have V is equal to I into R. So substituting that, I get V is equal to I multiplied by 2.4, which works out to be 1.5 into 2.4, which is nothing but 3.6 volt. We have the potential difference across 2.4 resistor as 3.6 volt. Let's consider this one. When a high resistance voltmeter is connected directly across the cell, when a high resistance voltmeter is connected directly across the cell, its reading is 2 volts. So the voltmeter reading is given as 2 volts. If the cell is sending a current through an external resistance of 4 ohms, the reading falls to 0.8 volts. So there is a fall in the reading when it is sending it through an external resistance. You are asked to calculate the internal resistance of the cell. Again, the network is given to you, wherein we have the battery, we have the external resistance, we have another external resistance through which the voltmeter has been connected. So by Ohm's law, I have the relation V is equal to IR. Using that relation, I have 0.8 is equal to I multiplied by 4, which results in I giving the value of 0.2 ampere. Now, electromotive force minus the terminal voltage is equal to I multiplied by small r. So we know this relation also. Electromotive force minus V, terminal voltage, is equal to I into R, small r. So I get 2 minus 0.8. 2 minus 0.8 is equal to 0.2, that is I, multiplied by R. Substituting, I get the value of R as 6 ohms. So I get the value of internal resistance as 6 ohms. Talking about this chapter as far as the board point of view is concerned, as you have seen already that most of the times you are having numericals that are based on this. The coverage is around 6 marks in the boards. A very simple chapter to tackle with. It is divided into section A and section B. Section A, you have theoretical questions for 2 marks, and as far as section B is concerned, you may have a numerical that is worth 3 marks or 4 marks, normally appearing in question number 9. But a very simple chapter to deal with as far as your boards are concerned. So with this base of theory, if we go on to the questions that had appeared in the board examination. We go year by year. So you'll come to know what exactly have appeared as far as the boards are concerned. The weightage for this in the boards is around 4 to 6 marks, wherein you have it divided into two parts. One is your section 1, wherein you have 2-mark questions. One is your section 2, wherein you have a 3-mark numerical normally asked in section B. In section 1, it's a theoretical question. State Ohm's law, what are the factors on which resistance depends, and so on. Let's consider this one, which had appeared in 2005. Which physical quantity does an electron volt measure? Which physical quantity does an electron volt measure, and how is it related to the SI unit of this quantity? How is it related to the SI unit of this particular quantity? Obvious answer over here is electron volt measures energy. Electron volt is a measure of energy, and it is related to its SI unit by the relation 1.6 into 10 to the power minus 19 joule is equal to 1 electron volt. 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule, because joule is a SI unit of energy. So we are correlating electron volt with joule by this particular conversion. Talking about 2006, mention the factors on which resistance of a wire depends. See, I told you, this is a very simple question that are asked in this particular sector. The answer for this should be the resistance of a wire depends on. Now, whenever they are asking you a question of dependency, remember you're always going to talk about the proportionality, whether it is directly proportional or inversely proportional. Considering directly proportional and inversely proportional, we say that the factors on which the resistance of the wire depends are, it is directly proportional to the length of the wire. Greater the length of the wire, more is the resistance of the wire. Similarly, inversely proportional to the area of cross section. That means thicker the wire, greater is the cross sectional area. Greater the cross sectional area, less is the resistance offered, because the spread of atoms and molecules is going to be so nice that it's going to allow the charges to flow through. However, if you have it in a condensed form, that is, the area of cross section is less, definitely the arrangement of atoms and molecules will not permit the charges to flow across. So the resistance offered in case of a thinner wire is going to be much more as compared to a thicker wire. How about 2007? It was a graphical question, a very good question, which we call as similar to your application-based question. It makes you think. You are given a V versus I graph, voltage versus current graph, in which they are connected either in series or parallel, and then you are asked to determine which out of the two, the graph A or graph B, represents a parallel combination. And they are asking you to justify your answer. Now remember, when we studied V versus I graph, we definitely said that the graph is a linear relation for ohmic conductors. And since it's a linear relation, we are getting straight line graph. The moment we get a straight line graph, we know interpretation of a straight line graph is that slope is a constant. And when slope is a constant, the slope here represents only the resistance of the conductor. In case of series, the total resistance of the conductor increases because it is the sum total of individual resistances. That was the third conclusion we had in series combination. However, in parallel combinations, we see that it is the sum total of reciprocals. So definitely there is going to be a decrease in value as far as parallel combination is concerned. So lower the slope, it becomes a parallel combination. Greater the slope, it becomes a series combination. So out of A and B, which of the two graphs has got a lower slope? Obviously it is A. And since A has got a lower slope, we say that it is A graph that is representing a parallel combination. Such a simple question, but it had appeared for almost 2 marks. But this one, again, this is also a graphical question which came in 2008. Sketch a graph to show the change in potential difference across the ends of a conductor and the current flowing through it. That means which graph have you to draw here? Yes, it is the graphical representation of Ohm's law. Whereas we plot the graph of V versus I. When we plot a graph of V versus I, we see that we get a straight line graph passing through the origin. When it is a straight line graph passing through the origin, slope is nothing but change in the y coordinates upon the corresponding change in x coordinate. Change in y coordinate is nothing but change in potential difference. Change in corresponding x coordinate is nothing but the change in current. So change in voltage upon change in current is the slope, which is nothing but the resistance of the conductor. We are going ahead with the solved board numericals now in this case. Let's consider the year 2002. There was a network that was put across and they are asking you to find out the ammeter reading. A cell of EMF 1.5 volt and internal resistance 10 ohm is connected to a resistance of 5 ohms. Is connected to a resistance of 5 ohm with an ammeter in series. Now this ammeter that is connected in series is going to measure the current in the circuit. You are asked to find out the reading in the ammeter. We are applying the universal law, that is Ohm's law. Using Ohm's law, I get EMF is equal to current multiplied by total resistance. So if I substitute the values, I get 1.5 is equal to current multiplied by the total resistance. What is the total resistance? 5 plus 10. Substituting again, I get 1.5 is equal to current multiplied by 15. So therefore current works out to be 0.1 ampere. The reading in the ammeter works out to be 0.1 ampere. Very simple sum as far as this is concerned. But then they do ask these questions. That's what we say always, that this chapter has a more coverage for the boards as compared to the theoretical part. Talking about 2003, we had this network that was given wherein you have two resistors that are connected in parallel, which is connected to an ammeter, a switch and a battery as shown in the circuit diagram. You're asked to find out three parts wherein you're asked to find out the equivalent resistance between points P and Q. You're asked to find out the reading in the ammeter again, and you're asked to find out the electrical power that is generated between P and Q. Remember, we have done in electrical appliances, electrical power. So we are going to apply that over here also. So let's consider the first part, that is, we're asked to find out the equivalent resistance. While considering the equivalent resistance, we know that these two resistances are connected in parallel. When these two resistances are connected in parallel, the formula that we apply is R1 R2 upon R1 plus R2. If I have R1 R2 upon R1 plus R2, I substitute the value 6 multiplied by 4 divided by 6 plus 4, which works out to be 2.4 ohms. So I have the equivalent resistance as 2.4 ohms. The potential difference across P and Q. In order to find out the potential difference between P and Q, we use the Ohm's law here again, and then we have V is equal to IR. So I have the potential drop across P and Q as 2 multiplied by 2 into V. That works out to be 4 volts. Hence, applying Ohm's law again, as I said, we are using 4 is equal to I multiplied by 2.4. So I have to find out I in this case, the current. I is equal to 4 divided by 2.4. That is nothing but 1.67 ampere. We have the current, that is 4 upon 2.4, which is 1.67 ampere. The reading in the ammeter works out to be 1.67 ampere. Now, as I said, we are thinking about electrical power also. Electrical power here in this case is I squared R. I squared R was a formula for electrical power which we studied while studying electrical appliances. Substituting the value of I as 1.67 square multiplied by 2.4. So I get that as 6.67. And the unit of electrical power is watt. So therefore the electrical power between points P and Q works out to be 6.67 watt. Now this appeared again in 2005. We have studied these numericals that have been coming in 2003, 2004, 2005. This also appeared in 2005 for about 2 marks. It says 4 resistors of 2 ohm each. 4 resistances of 2 ohm each are joined in such a way, end to end, so that they form a square A, B, C, D. You're asked to calculate the equivalent resistance of the combination between any 2 adjacent corners. Adjacent corners could be A to B, B to C, C to D, D to A. So these are the adjacent corners. If I have to calculate resistance between A and B is given as 2 ohms. Resistance between A, B, C and D is 6 ohms. Resistance between 2 adjacent points is given as AB and ABCD will be in parallel. So if I connect this in parallel, I have the equivalent circuit diagram. 1 upon R is equal to 1 upon R1 plus 1 upon R2. That is 1 upon 2 plus 1 upon 6. That is 8 upon 12. But this is 1 upon R. So if I have to find out R, it is 12 upon 8. That is the reciprocal of the previous one, which is 1.5 ohms. So I get the equivalent resistance of the combination as 1.5 ohms. Coming down to 2006 again. Again, a very simple question that was put across depending on the length and the thickness of a wire. A wire of uniform thickness with a resistance of 27 ohms. So I have a wire of uniform thickness, a uniform cross-section of area, which has got a resistance of 27 ohms, is being cut into 3 equal parts. So I'm cutting the wire into 3 equal parts or sections, and then joined in parallel. So I'm cutting it into 3 parts, then connecting them in parallel as shown. Find the resistance of the combination. So what will be the value of resistance when it is cut into 3 parts? 3 equal parts of uniform thickness. Yes, definitely the resistance will be 1/3 the original resistance. Resistance of each part will be 1/3 of the original resistance. So resistance of each part will be 27 by 3, that is 9 ohms. So all these 3 resistances have 9 ohm as the resistance. We are connecting this 9 ohm resistance in parallel now. So we have 3 resistances of 9 ohm that are connected in parallel. So I have the equivalent circuit diagram as 1 upon R1 plus 1 upon R2 plus 1 upon R3. So we have it as 1 upon 9 plus 1 upon 9 plus 1 upon 9. If I solve this, I get the value of R as 3 ohms. So the equivalent resistance of the parallel combination works out to be 3 ohms. As we saw different questions that were asked in boards, we have also one more year that this particular question had appeared, that is in 2008. Let's consider the question that appeared in 2008. Again, the network is given to you. You're given 3 resistances that are connected across a battery source, and an ammeter is also connected in the series. 3 resistors, 6 ohms, 2 ohm and 3 ohm are respectively joined together as shown in the network. The resistances are connected to an ammeter and to a cell of EMF 6 volt. You are asked to calculate the effective resistance of the circuit and the current drawn from the cell. Effective resistance of the circuit and the current drawn from the cell. Looking at the circuit diagram, we know that the 4 ohm and 2 ohm resistor is in series with 6 ohm resistor. So if I have to calculate the equivalent resistance, I put it as effective resistance of the circuit can be calculated as a parallel combination of R1 with R2 plus R3. So that becomes R1 into bracket R2 plus R3 divided by R1 plus R2 plus R3. If I substitute the value, I get it as 6 multiplied by 6 divided by 6 plus 4 plus 2, which is 36 upon 12, that is 3 ohms. Also, according to Ohm's law, I have V is equal to IR. Using that particular relation, I get 6 is equal to I multiplied by 3. So I get the value of I in this case as 2 ampere. So therefore the current drawn from the coil is 2 ampere. Let's take a recap as to how exactly we are going to memorize this particular chapter. First, what did we study? We studied what is potential at a point, then potential difference, then current, resistance, resistivity, conductivity, conductance. With all these basics of 9th put across, we went in for the universal law, that was the Ohm's law. Physical conditions of a conductor remaining constant. Current flowing through the conductor is directly proportional to the potential difference between the two ends of the conductor. Mathematically, V is equal to IR. Then we studied the combinations of series and parallel, when we said that the effective resistance in case of a series circuit is R is equal to R1 plus R2. In case of parallel circuit, 1 upon R is equal to 1 upon R1 plus 1 upon R2. In case of series circuit, the same current flows through the entire circuit. In case of parallel circuit, the potential drop is constant. In case of series circuit, again, we said that V is equal to V1 plus V2. In case of parallel circuit, we had I is equal to I1 plus I2. So all these put together we went across to study the networks. We also studied the concept of EMF and internal resistance.